So, in today's lecture, we're going to look a little bit deeper into energy, in particular, the E-dis portion of it, energy dissipated. Now, a quick reminder if I didn't already cover it, mechanical energy is the sum of the system's kinetic and potential energy. In this case, the potential is both gravitational and elastic potential energy. So, it's all of these three. E-dis is separate from that. But let's talk a little bit more about it. Conservative versus non conservative forces. A force is considered non conservative if it creates a change in the mechanical energy. In other words, it generates some E-dis, some E energy dissipated. Some examples of this: frictional force, drag force, any kind of resistive force always tends to generate heat, which is going to convert some of our mechanical energy into energy dissipated. One funny thing about this is once you end up with E-dis, it's very difficult to make it back into useful mechanical energy. The heat, for example, that your car generates after it's been driving, either electric or gasoline powered, you can't easily take that heat and make it into useful mechanical energy. You can't use the heat to speed up your car again. So it's often considered irreversible. So work done by non-conservative force, once it's into E-dis, you can't convert it back. It also, though, depends upon the path that you take. And this is where it gets interesting. If there is friction, which one of these two paths will do more work or make more E-dis? Well, if you remember, work is equal to force times displacement times the cosine of the angle. For friction, it always acts against the motion or potential motion, and it's independent on the velocity. So in which case does this have a greater E or delta x, greater displacement? The answer is, if you can't already see it, it's going to have a greater displacement in the lower path, which means if you have the same force of friction acting through a greater displacement, there is going to be more energy converted to E-dis if you slide it along the bottom path. And this is assuming there's friction. If there's no friction, you're right. It doesn't matter which path you take, but the bottom path is going to take more energy. It's going to create more E-dis. And we've already talked about it. Here's another quick example. If you've got a ramp and you let a ball go down it, and you got another ramp from the same height and let the ball go down the second one, if there's friction, if there's no friction, same velocity at the bottom. But without friction, the one that goes through a longer path is going to have a lower velocity at the end. So let's do a quick example on this one. A 5-kilogram ball slides down a ramp that's 10 meters tall. In both cases, experience a kinetic force of 10 newtons. One slides 15 meters, the other one's 25 meters. How much energy is converted to heat in both cases? Well, in the first case, it's going to experience, it's got 10 newtons acting on it. The first one is 15 meters long. 15 times 10 times the cosine of 180. The force of friction is going to do 1,500 joules of work. Technically negative 1,500. But what's going to happen then? My E-dis for the first one, I'm going to just do E sub D, is going to be 150 joules. The second one, 25 meters in length, E-dis for that one, is going to be, it's going to lose 250 joules, 25 times 10. What's the final velocity of the ball in each case? Well, you can very quickly work it out. You're going to start out with gravitational potential energy, plus the work done by friction, which is going to be technically negative, is going to equal the final energy in this case, which is all going to be kinetic. I won't actually do this one for you, but I will actually kind of remind you that the work done by friction in both these cases is negative. Initial energy is going to be 500 joules. And so I'll do the first one just for you real quick. Plus the amount of work done, negative 150. So our final kinetic energy in this case is going to be 350 joules. If 350 joules is equal to 1/2 mv squared, or the mass is 5, you can very, very quickly work this one out. I may not be able to do a square root real quick, but multiply both sides by 2. 700 divided by 5 should be 140 is equal to v squared. And for all practical purposes, v is going to be about 12 meters per second to 2 sig figs. You can repeat this again. The thing that's going to change for your second one is the amount of energy lost. It'll be 250 in the second case. Kinetic friction, then, is an example of a non-conservative force. And you can work out, and I've got a couple of sample problems here. We've already done one like this, so I'm going to skip this one. But I want you to take a look at this next problem. Angel and Brittany both start from rest at the same height at the top of the hill. They start sliding towards the bottom of the hill at the same time. Assuming that air resistance and friction are negligible, does Angel or Brittany have a greater speed at the bottom of the hill? Or do they have the same speed? Justify your claim with evidence and reasoning. Well, if you haven't yet figured this one out, the evidence you have, they both start out with the same gravitational potential energy. If there's no friction, there's no work being done, which means they both have to end up at the exact same final kinetic energy. I was just checking here real quick. Do they have the same speed? Well, that depends on their mass. If they have the same mass, yes, they'll have the same velocity because they have the same final kinetic energy. However, if one of them has a larger mass, they will be going a little slower than the other one. So in your worksheet tonight, you're actually going to do the energy flow diagrams, the bar graphs we were working with before, but this time we're actually going to do it with quantitative numbers. So let me quick show you. In this case, you've got a cart moving initially and it's going to run into a spring and stop briefly. You have to define your system. In this case, I'm going to say that my system is the cart and the spring. And we have to figure out how far the spring is compressed, so I'm going to do my math real quick. Car starts out with kinetic energy. That's 112 joules. In the end, all that 112 joules, or 112.5 joules, is going to be converted into elastic potential energy, 1/2 kx squared. Plugging in our spring constant, we'll discover our spring is compressed 2.1 meters. What's our energy diagram look like? Well, we start out with kinetic energy, we end up with gravitational potential energy, and all of it stays inside of our system. So there is no energy flow diagram at all. I'm also assuming that there's no friction, so no E-dis is generated. What if we change my system to just the cart? Well, all my calculations stay the same down below for how far the spring is compressed. But now my energy diagram would just be kinetic energy to begin with and no energy at the end. The cart is not moving. So now my energy flow diagram, I'd have to have 112.5 joules leaving the cart. Yeah, it's going to the spring, but because spring is no longer part of my system, it looks like it's leaving the system. Again, the direction you draw that arrow is not important. It's just got to leave that circle. What if I made my system the spring? Well, now the spring starts out with no energy, but ends up with elastic potential energy. What would my energy flow diagram look like? It would be 112.5 joules flowing into the system. It's 112.5 joules larger at the end than what it started. Take a look at this second problem. Determine the final velocity of the cart, assuming that 10% of the energy is dissipated by friction. So we start out with gravitational potential energy. I'm going to define my system as the cart, track, and the Earth. Now, a quick note on the Earth. We need the Earth if we're going to talk about gravitational potential energy. Without the Earth, we have no reference, nothing pulling down on it. If you just had the cart, you can't have gravitational potential energy. This is important. Working out, we start out with 1,000 joules of gravitational potential. And now here's the critical part. 10% is dissipated. So that means that 10% of this 1,000 is converted to E-dis, meaning I'm only left with 900 afterwards. And that's going to be converted into the final kinetic energy of the car. Plugging in the numbers, you'll discover the final velocity of the car is about 9.49 meters per second. Solving this one, we start out with gravitational potential energy, 1,000 joules. We end up with 900 joules of kinetic, and then the rest of it ends up as E dis. There's 1,000 joules to start out with, 1,000 joules in my system to end with. So there's no energy flow diagram in or out of the system. What if we change the system to just the cart? Well, this gets a little bit more exciting. All we end up with, remember, without the Earth involved, we can't have any kind of gravitational potential energy. And I'm going to argue that probably most of the heat went outside the system, either to the air or to the track, maybe some went to the cart. This can change your system a little bit. But I'm going to argue that almost none of the heat went into the cart. And so I'm going to say then that there's no E dis, and 900 joules of energy must have entered my system. Why? I have 900 more joules at the end in the final state than I started out with. And now finally, take a look at the number 5. A 200 kilogram box is pulled at constant speed, that's important, by the little engine pictured below. The box moves a distance of that across the level horizontal surface. Draw a force diagram of all the relevant forces acting on the box. Well, it's a 200 kilogram box, so there'll be 2,000 newtons of force of gravity. 2,000 newtons will be. So now we know the force, normal force is 2,000. Reminder that the force of kinetic friction is just equal to mu sub k times normal force. In this case, if you quickly do the math, 2,000 times 0.2 should give you 400 newtons. Since it's moving at constant speed, what must be the tension on the system? The answer is the rope must have a tension of 400 newtons to keep it moving at a constant speed. B, construct a qualitative energy bar flow diagram for the situation. Be sure to include or specify your system. I'm going to arbitrarily just say the system is my box. In that case, the kinetic energy beforehand equals the kinetic energy afterwards. But since there is friction, it probably also generates some E dis, meaning the energy flow diagram, there has to be energy entering my system. Why? The total final energy is greater than my initial. C, how much energy is transferred? Whenever you see the words energy and transferred together, there's only one thing that can transfer energy from one system to another, and that's work. And again, remember, work is defined as force times displacement times the cosine of the angle between those two. In this case, the angle is 0. Why? The displacement is in the same direction as the force that the engine's exerting along that rope, the tension. And so if you solve it, you'll discover that the work done by this engine when it pulls that 2.5 meters up above here is just going to be 1,000 joules. D, what type of motion would occur if the engine now pulled with a force of 500 newtons instead of 400? So you very quickly can figure out, oh yeah, I'm only going to draw the horizontal ones. Friction's going to stay at 400, tension's now 500. Using F net equals ma, 500 minus 400 equals 200 times a, you'll discover that the acceleration, it's going to accelerate at 0.5 meters per second squared towards the motor. Hopefully that makes sense. Your mini lab is actually exploring the conservation of energy. What are you going to do? You're going to hang a known mass over here at some height above the floor. And we're going to use the floor as h equals 0. And what's going to happen here? Well, the system starts out with gravitational potential energy. We're going to assume that there is very little friction, so work done is going to be 0. And then what's the final energy of the system? Well, it's all going to be kinetic. Is it the kinetic energy of the hanging mass or the car? The answer is it's actually both of them. And so we'll take the final velocity of the cart to actually figure that out. As this thing's moving, the velocity is going to increase and increase and increase. You want the maximum velocity of the cart. That'll be the maximum velocity of the hanging mass just before it hits the floor. For those of you who may not be able to do the lab, I will link some data to the spreadsheet or to the assignment sheet so you can actually work on it if you're actually not doing the lab. Good luck with this. Have fun. Talk to you soon.